Hello, everyone, and welcome to Challenge for Solar Power. Electromagnetic waves. There are three types of electromagnetic waves emitted by the sun: visible light, infrared radiation, and UV radiation. As you can see from the electromagnetic wavelength diagram in the corner, infrared radiation has the longest wavelength of the three, followed by visible light, with UV radiation having the shortest wavelength. Within UV radiation, there are three subtypes: UVA, UVB, and UVC. Of these three, UVA has the longest wavelength, with UVB in the middle and UVC having the shortest. The diagram also transitions from green to red, with the green representing non-ionizing radiation and the red ionizing radiation. Ionizing radiation removes electrons from molecules and atoms as it passes through them. The transition between these two occurs within the UV band, and the radiation within and to the left of it is non-ionizing, and to the right is ionizing. Of the radiation that travels from the sun towards the Earth, about 21 to 25% gets absorbed by the upper and lower atmospheres. This includes all of UVC and most of UVB waves. About 30% of what is not absorbed by the atmospheres gets reflected by things on Earth, and the remaining about 45 to 49% is absorbed by things on Earth. Most of what is absorbed is comprised of visible light. Photovoltaic solar panels. Of all of the electromagnetic waves that reach the Earth, some get absorbed by solar cells. These cells are composed of a semiconductor material, which is a solid with an electrical conductivity between that of a conductor and an insulator, and its resistance decreases as its temperature increases. Within electromagnetic waves are photons, which are either reflected by, pass through, or get absorbed by the cells. It is the photon that is absorbed that is used to generate electrical energy. As photons are absorbed, energy within the cells builds up, and once it reaches a breaking point, the electrons within the material are knocked free. The manufacturing of the cells causes the front surface to be more available to the free electrons, and the induced charge difference between the front and back creates a voltage potential. From there, electrical conductors absorb the electrons and pass them through a circuit, and the photonic energy has now become electrical energy. UV rays provide the most photonic energy, followed by visible light, and then infrared radiation. Benefits. One of the benefits of solar energy is that it is a clean form of energy, and the reason for this is because the byproduct created is heat and not gases. Another one of the benefits is, of course, the energy produced. In 2022, large-scale solar panels, meaning industrial level, produced roughly 143 billion kilowatt hours throughout the year. And small-scale solar panels, meaning residential type, produced about 59 billion kilowatt hours. However, not everything is smooth sailing. Efficiency issues. The efficiency of a form of energy is how much energy is used to convert to electrical energy versus the amount of electrical energy that is generated. It is the percentage of input energy that the output energy comprises. The efficiency of commercially available solar panels was about 15% in 2015 and is now currently up to 25% for state-of-the-art models. The predicted current efficiency limit is 33%. This means that only about 33% of the amount of solar energy that is put into the solar panels actually becomes electrical energy. This is the equivalent to the efficiency of coal, which is already in wide use. And considering that the cost of installing a solar panel is between $4,500 and $36,000 with an average of $16,000, before more widespread usage of solar panels becomes popular, the efficiency issue needs to be dealt with. And in addition to efficiency being an issue, the access to the sun that even allows the efficiency to be utilized is also a considerable hurdle. This is because peak sun hours differ by region and time of year, which means that access to the sun for the solar panels to generate electrical energy is inconstant, further damaging the effectiveness of solar energy. But there are measures that can be taken to combat the issue of efficiency. Efficiency improvement, photovoltaic thermoelectric systems. As I mentioned earlier, the byproduct of solar energy is heat. And while this does not pose a threat to the environment, it does pose a threat to the photovoltaic panels themselves. This is because excess heat reduces efficiency and increases the cell aging rate. A method to both combat the heat issues and the efficiency issues is to utilize a photovoltaic thermoelectric system. Within this system, UV and visible light would be directed to the PV panels, where the photonic energy would be converted into electrical energy. And the infrared radiation would be directed to the thermoelectric generator, where photonic energy would become heat energy and heat energy electrical energy. With the thermoelectric generator, two different materials would be used, acting as a hot side and a cold side, respectively. And since they would be directly connected due to material properties, a voltage proportional to the temperature difference would be generated. Now you're probably wondering how exactly the different electromagnetic waves would be directed to the different parts of the system. This would be done through spectral splitting. The spectral splitting would be initiated through a refractive device, wherein light is refracted through a set of prisms arranged such that the refracted light becomes concentrated onto a focal point. These prisms are made of a material with dispersive properties to separate different spectral bands to different locations. Since the infrared photons contain an energy below the band gap energy of the photovoltaic cells, they would be directed to the heat absorber. As I mentioned earlier, a thermoelectric generator requires a hot side and a cold side. The cold side would be provided by a daytime radiative cooling module, which will lower the temperature of itself to below ambient temperature by emitting heat to space with a wavelength of 8 to 13 micrometers without extra energy consumption. Another one would also be placed above the PV cells in order to prevent them from being damaged by the heat buildup. This setup could improve the efficiency by 3.6% to 10%, which may not seem very large. However, in terms of industrial solar panels, 5.148 billion kilowatt hours to 14.3 billion kilowatt hours generated annually. Meanwhile, in 2020, the average apartment used only about 14,830 kilowatt hours. A small percentage can be a big improvement. To wrap everything up, here are the references that I found while researching. If you found this topic interesting, feel free to take a look. Have a great day/night, everyone.